One of the nearest galaxies to us is Andromeda, and it is for this reason that scientists have focused a lot of their research on it. However, nothing prepared them for the shocking discovery the new James Webb Space Telescope recently made about the galaxy. What have scientists just learned about our neighboring galaxy, and how does it affect our one and only planet? Stay tuned as we dive into JWST's new terrifying discovery about the Andromeda Galaxy that changes everything. The Andromeda Galaxy, our Milky Way's closest neighbor, is the most distant object in the sky visible with the naked eye, but only on a clear night from a very dark location. The visible fuzzy patch of stars is about the length and half the width of the full moon. Only with significant magnification can you tell it is 6 times that length in fullness. Andromeda, like the Milky Way, is a spiral galaxy with a concentrated bulge of matter in the center, surrounded by a disk of gas, dust, and stars, and an enormous halo. Though Andromeda has 1 trillion stars compared to the Milky Way's 250 billion, our galaxy is actually larger because it's thought to contain more dark matter. Humans have long known about Andromeda. In his Book of Fixed Stars, the Persian astronomer Abd al-Rahman al-Sufi described the galaxy as a small cloud in 964, the first known report of our nearest neighbor. When Charles Messier named it M31 in 1764, he incorrectly attributed the discovery of what was then known as a nebula to the German astronomer Simon Marius, who made the first telescopic observation of the object. And Isaac Roberts took the first photographs of Andromeda in 1887. This distant galaxy was part of the great debate between American astronomers Harlow Shapley and Heber Curtis in the 1920s. At the time, astronomers believed the Milky Way contained the entire universe, including the strange patches known as nebulae. Curtis, however, had discovered several novae in Andromeda and claimed that it was a separate galaxy. The debate was not resolved until 1925, when Edwin Hubble discovered a Cepheid variable, a star with characteristics that allow for precise distance measurements within Andromeda. Because Shapley determined that the Milky Way was only 100,000 light-years across, Hubble's calculations revealed that the fuzzy patch was too far away to be contained within the Milky Way. Hubble then used his measurements of galaxies' Doppler shifts to conclude that the universe was expanding. Then, when Walter Baade, who was the first to observe individual stars in the central region of the galaxy and discovered 2 different types of Cepheid variables in the 1940s, the calculated distance to Andromeda doubled. After radio emissions were detected by Hambry Brown and Cyril Hazard at Jodrell Bank Observatory in the 1950s, radio maps of Andromeda were created. And in recent years, we have gained an even better understanding of the size of the Andromeda Galaxy. The Hubble Space Telescope observations in 2015 revealed that a halo of material surrounding Andromeda is 6 times larger and 1,000 times more massive than previously measured. At the time, astronomers speculated that the Milky Way might also have a halo, and that the halos of the 2 galaxies may be merging. This is in addition to revised size estimates made in 2005 and 2007, based on observations of stars and star motions. Scientists released the most detailed image of Andromeda ever in 2015, using a mosaic of Hubble Space Telescope images. The image was composed of 7,398 exposures taken over 411 telescope pointings. The image revealed more than 100 million stars, as well as dust structures and other features within the galaxy. Scientists said at the time that the images would aid in extrapolating the structure of spiral galaxies that are even further away from Earth, making them more difficult to observe in such detail. And Andromeda's black hole activities were also investigated. Scientists discovered 2 supermassive black holes orbiting each other in late 2017. The research team stated at the time that these black holes were likely the most tightly coupled of any known supermassive ones. In 2013, a search using NASA's Chandra X-ray telescope yielded 26 black hole candidates in Andromeda, making it the largest catch of such candidates ever discovered in a galaxy other than our own Milky Way. And then in 2016, NASA's Nuclear Spectroscopic Telescope Array-New Star, which specializes in X-ray observations, discovered 14 more black holes. In 2017, scientists discovered a possible pulsar, a dead star that spins rapidly in Andromeda. The X-ray source was discovered by NASA's SWIFT satellite as Swift J0042.6 plus 4112 and then classified by NuSTAR. The light spectrum of this object appears to be similar to that of pulsars in the Milky Way, according to newer observations. Other research that has been conducted on the Andromeda galaxy has been tracking star birth and death in infrared wavelengths in 2011, discovering gamma-ray radiation in 2017 that could be an indication of dark matter, a substance known only through its effects on ordinary matter such as galaxies, and spotting a ring of dwarf galaxies around Andromeda in 2013, something that could also be present around the Milky Way. However, with the JWST being fully operational, scientists now have a new tool to observe and expand our knowledge of Andromeda. One of the things that scientists can now study with the JWST is the newly detected mass migration of stars converging on Andromeda. Astronomers understand that galaxies grow over time by merging with other galaxies. It's happening in our galaxy right now. The Milky Way is gradually absorbing the Magellanic Clouds as well as the Sagittarius dwarf spheroidal galaxy. However, astronomers have discovered evidence of an ancient mass migration of stars into another galaxy for the first time. They discovered over 7,000 stars in Andromeda M31, our nearest neighbor, which merged with the galaxy approximately 2 billion years ago. The growth and evolution of galaxies is a hot topic in astronomy, which is one of the reasons the James Webb Space Telescope has received so much attention recently. One of the JWST's primary scientific goals is to look back in time to the universe's earliest galaxies to learn how they grew and evolved into what they are today. However, it is not the only telescope that can shed light on the problem. The dark energy spectroscopic instrument DESI made these new observations of Andromeda and the inward migration of stars. It was designed to assess the impact of dark energy on the expansion of the universe. It accomplishes this by collecting optical spectra from tens of millions of objects, primarily galaxies and quasars, and then creating a 3D map of the results. The DESI spacecraft is similar to the more well-known Gaia spacecraft. Gaia's goal is to precisely map the positions and motions of billions of stars in the Milky Way. And the data from Gaia led to a slew of new discoveries about our own galaxy. However, it is limited to mapping stars in the Milky Way. However, for the first time, astronomers have at least a partial map of the stars in Andromeda thanks to DESI. And that map, which includes the motions of nearly 7,500 stars in the Andromeda galaxy's inner halo, is revealing their history. These findings are published in the paper DESI Observations of the Andromeda Galaxy, revealing the immigration history of our nearest neighbor. It will be published in the Astrophysical Journal with Arjun Day, an astronomer at the National Science Foundation's NOIR lab, which is responsible for DESI, as the lead author. According to DESI, another galaxy merged with Andromeda about 2 billion years ago. The positions and motions of approximately 7,500 stars measured by DESI indicate that they originated in another galaxy. The new observations of the Andromeda Galaxy reveal evidence of a galactic immigration event in exquisite detail. They show that although the night sky appears to be static, the universe is a dynamic place. Over cosmic history, galaxies like M31 and our Milky Way have been built from the building blocks of many smaller galaxies. A similar merger occurred between 8 and 10 billion years ago in the Milky Way. The majority of the stars in our galaxy's halo were born in another galaxy and joined the Milky Way as a result of an ancient merger. By closely observing this similar, more recent merger event in Andromeda, astronomers can learn more about the Milky Way's ancient history. Scientists have never seen this so clearly in the motions of stars before, nor have they seen some of the structures that result from this merger. The emerging picture is that the Andromeda Galaxy's history is similar to that of our own galaxy, the Milky Way. A single immigration event dominates the inner halos of both galaxies. For the first time, we see the structures that arose as a result of the merger. The expected observational signatures of galactic migration include debris streams, shells, rings, and plumes. The expected outcomes of merger interactions between large galaxies and their companions. We see clear kinematic evidence for shell structures in the giant stellar stream at northeast shelf and western shelf regions. The kinematics match the predictions of dynamical models developed to explain the spatial morphology of the inner halo. The findings support the hypothesis that much of the substructure in M31's inner halo was created by a single galactic immigration event 1 to 2 billion years ago. While hints of coherent structures have previously been detected in M31, the authors write in their paper this is the first time they have been seen with such detail and clarity in a galaxy beyond the Milky Way. The observations reveal an intricate, coherent kinematic structure in the positions and velocities of individual stars, streams, wedges, and chevrons. Though the positions and velocities of the 7,500 stars were important in these discoveries, so was stellar metallicity. The team discovered high metallicity stars in all of the merger's substructures. We find significant numbers of metal-rich stars across all of the detected substructures, implying that the progenitor galaxy or galaxies had an extended star formation history, possibly more representative of more massive galaxies, the authors of the study concluded. The study emphasizes similarities between Andromeda and the Milky Way, bolstering the theoretical idea that mergers are important in galactic evolution and growth. M31 is remarkably similar to the Milky Way in that the inner halos of both galaxies are dominated by stars from a single accretion event. Indeed, a recent study of the kinematics of Milky Way stars near the Sun reports chevron-shaped kinematic substructures that are reminiscent of those reported here. And the power of DESI is on full display in this study. The results are the results of DESI's ability to collect spectra from 5,000 objects at the same time. This complex instrument is the world's most powerful multi-object survey spectrograph, capable of reconfiguring its 5,000 separate focal planes in less than 2 minutes as it slews between targets. It was created to map the large-scale structure of the universe and how dark energy fuels its expansion by measuring the spectra of over 40 billion distant galaxies and quasars. But it's also showing us how galaxies merge over time. According to the team, this science could not have been accomplished at any other facility on the planet. They praised DESI's incredible efficiency, throughput, and field of view, making it one of the best systems in the world for surveying the stars in the Andromeda galaxy. In only a few hours of observing time, DESI was able to surpass more than a decade of spectroscopy with much larger telescopes. If DESI can pull off such a feat, imagine what the more powerful JWST will do. And another thing about Andromeda that the JWST will help scientists learn is the future collision of the galaxy with our own galaxy. Yes, you heard that right, Andromeda will crash into the Milky Way. One day, far in the future, Andromeda will be bright in our sky, growing larger and larger as it gets closer and closer to us. And even though the two galaxies are still 2.5 million light-years apart, the eventual merger of our two galaxies has, in fact, already begun. The Andromeda galaxy is currently speeding towards our Milky Way at about 70 miles or 113 kilometers per second. With this in mind, our merger will take place in 5 billion years. However, new research published in the peer-reviewed Astrophysical Journal in August 2020 revealed that the collision between our galaxies is already underway. The news about the Andromeda galaxy came from Project Omega, which uses the Hubble Space Telescope to study the Andromeda galaxy's surroundings in deep space. Omega is an abbreviation for Absorption Map of Ionized Gas in Andromeda. The Andromeda galaxy, our Milky Way, and other galaxies are all surrounded by a large envelope of gas, dust, and stray stars known as a galactic halo. The halos of galaxies are faint, so faint that detecting them is difficult. The halo of the Andromeda galaxy was measured by looking at how much light it absorbed from background quasars. They were surprised to discover that the halo of the Andromeda galaxy extends far beyond its visible boundaries. It reaches half the distance to our Milky Way, 1.3 million light-years, and even further in other directions, up to 2 million light-years. So do the halos of the Andromeda and Milky Way galaxies intersect? Well, it turns out that we can't easily measure the properties of our galaxy's halo from our vantage point inside the Milky Way. However, because the two galaxies are so similar in size and appearance, scientists believe the Milky Way's halo will be similar as well. In other words, the faint halos of the galaxies appear to have begun to touch one another. Thus, in a sense, the collision between our two galaxies has already begun. Now, each galaxy, the Milky Way and Andromeda, has a central supermassive black hole. Over millions of years, these black holes will eventually spiral into one another and converge near the center of the new formed galaxy. And when two supermassive black holes approach each other by 1 light year, they will begin to strongly emit gravitational waves, which will radiate additional orbital energy until they merge completely. The gas absorbed by the combined black holes could form an active galactic nucleus. If this occurs, an enormous amount of energy will be released. So, what is the future of our solar system, you might wonder? According to current calculations, there is a 50% chance that in a merged galaxy, the solar system will be swept out 3 times farther from the galactic core than it is now. Our galaxy is divided into spiral arms, and the Sun is located in one of them, known as the Orion Spur. If we were flung further out, our solar system would land right at the tips of this arm's fingers. However, scientists also predict that the solar system could be ejected from the newly formed galaxy at some point during the collision. Of course, humanity would be long gone by then, providing some solace. Such an event would have no negative impact on the solar system, and the chances of any disruption to the Sun or planets themselves are remote, assuming no planetary engineering. By the time the two galaxies collide, the Earth's surface will have become far too hot for liquid water to exist, putting an end to all terrestrial life, but our planet will still be caught in the middle of this collision, and its view of the universe will never be the same. If we could still see the night sky, whether from Earth's hellish perspective or from the far reaches of the outer solar system, Andromeda would be growing larger in the sky, and in about 4 billion years, it could possibly stretch from horizon to horizon like a serene rainbow of dew.